So basically, they did a multi-omic analysis. This was longitudinal, obviously, over a pretty diverse age cohort. So what they found by essentially taking all the data, all the metabolites or the microbial taxa or whatever, and essentially what in statistics we call this dimensionality reduction. So you can do this with like a principal components or whatever, where you find which component is explaining most of the variance in the data. So it's a great way to fully utilize your data. And what Schneider found here was that looking at the dynamics explain variability over time. As you can see, metabolomics had the strongest correlation, meaning it's probably going to be in terms of like aging, because this is what this paper is focused on, the strongest predictor of aging, the most useful predictor of aging. See others like your clinical, like to your very right, upper right-hand corner, clinical lab testing, it wasn't even significant. And it explained about 16% of the variability compared to what metabolomics was doing at 66%. Even the microbiome, while it was significant, it was only about 40%. So this to me is actually really good support for what we're doing. I think what was pretty ingenious with how they approached this analysis was, doing this dimensionality reduction and forming these clusters if you go down to panel B. And what they did is looked at these different clusters so that here they could identify like which molecules were contributing, which microbial taxa, clinical markers, et cetera. You see, like with cluster 2, 4, and 5, it was the metabolome that was really informing these clusters. What they were able to do here was see when massive changes were occurring in these different layers. Like if you look at the metabolome, this is when aging was accelerating between the ages of 47 and 57. That's a very simple and powerful visual